this equation.
Yeah.
That's all. That's what we're working on. I forget how I define this now. I think the slow field was Z. Let's say it was like this. Remember how easy real space RG was in retrospect? So remember it was like, philosophically what you're doing is, doing one RG step. In this case, it's in the action, S to S prime. And then in real space RG, it was tracing out the degrees of freedom within the block. And here it's essentially taking this expectation value over the fast modes. And then you rescale. So in this case, you rescale momenta and the fields. So you're taking the slow field and turning it into the fast, or turning it into just the renormalized field with the scaling dimension, which I forget what it was off the top of my head. Okay, so we have this cumulant expansion, which goes to all orders in principle. And what we did was just evaluate the expectation value in the first cumulant, last class. And that got us these RG equations. And then when I identified, was it B, what? E to the delta L, or DL, if you will. Then we derived these the set of differential equations. I think that's where we were, roughly. So this Gaussian plus first order cumulant, gives a fixed point. And remember how you find the fixed point? This is parameterizing the RG, right? So it's like when you're going from whatever, R to R prime, U to U prime, and you're doing it in a very small step, sort of a vanishingly small step. This is the differential change in those parameters. So when those go to 0, that defines the fixed point. Okay, so in this case, it's trivial basically, because for this equation, it means U is equal to 0. Plug it in here, it means R equals 0. So that's the condition, if you will. dr du gives U star there, and where those stars denote the fixed point. So you remember when I gave general arguments for 2 dimensions? I was arguing that there's more than one fixed point. We still haven't seen that ever yet in this class. And it doesn't look like I'm going to get to it before reading week. So let's analyze these equations a bit more. Let's find okay, before I go to the second cumulant, which I will today, let's look at these first order equations and derive the scaling variables and look at the relevant and irrelevant operators and so on. Okay, so it's basically just practice with analysis of these RG equations. On the assignment, I might just give you a set of equations and say, there's two parameters, R, U, H, maybe whatever. And I'll say these are the differential equations, analyze the RG flows. So let's look at the analysis of the RG flows. So just to look back at your notes. Make sure I get this right. Km. Remember this equation? I defined delta Kn, say, is the difference between Kn prime after one RG step and the fixed point. That's related to, delta K before the fixed point via this matrix, which I called T. So this defines T. What are the K in our case? What are K? What are these K? It's not a trick question.
RNU.
It's RNU, yeah. So we just got all of our notation mixed up. But remember, there's a set of parameters. I was saying T and H before, like temperature and field. But R is just related to the reduced temperature, right? It's like T minus TC. And U is the strength of the phi-4 term, so the strength of the interactions. So we just need to, look at this, derive this T matrix, get the eigenvalues and eigenvectors, and that'll tell us how our RG flow diagram looks in terms of the axes. And then we can analyze it from there. So this matrix, again, just recall. We have eigenvalues and vectors. I called the scaling variables U. And I already have a U. And so I'm going to have U in terms of linear combinations of R and U. That's going to be confusing. So let me call them U tilde. Okay. If a tilde, it's a scaling variable. I know I also use U tilde for some intermediate RG step, but let me just define U tilde in this case as okay, so N, you're going to have 2. It's going to run over, just R and U up there. Okay, and this is delta, if you will, delta R and delta U. So you need those eigenvectors in order to form the scaling variables. And the scaling variables U tilde are the axes of your RG flow. So they're the directions along which you have relevant or irrelevant flows. right? So remember we derived u tilde prime. Oh, it's a big prime. And this was b to the y, I, which defined the scaling dimension, y. And you're imagining doing, you know, an infinite number of RG steps. You're iterating to infinity. So the reason you write it like this is so that if you can determine what y is, you know whether or not you have relevant or irrelevant flows. Relevant means you're pushing yourself, you know, successive iterations push yourself away from the fixed point, where if this is less than 0, then that scaling variable is irrelevant, and perturbations away from the fixed point, you just flow back into it. Okay? So let's do this for R and U. Oops. So I'll define delta R. So I'm just rewriting these equations. Instead of using K's, I'm using R's and U's. Okay, so three I1B squared. B to the 4 minus D. Okay. Right, so now I want to write this equation here in terms of T. So I'll define that T matrix. Let me write it like this. Okay. So now I need this thing. So I need the derivatives evaluated at the fixed point. So let's at R star, U star. Okay, so that T is easy enough to figure out. I have my equations for R prime and U prime up there. R prime, U prime. Okay, so that's your matrix. Eigenvalues. So I got two lambdas. One for R. Okay, now it's usually called T. Reduced temperature, right, is what's giving you R in the Landau theory. And then I'll call the other one U, I guess, which is B to the 4 minus D. So there's your scaling dimensions, right? YU. So one of these flows is going to become relevant or irrelevant at 4 dimensions. And so 4 dimensions is always special. So let's look at the eigenvectors. E to the I don't know, P or R, whatever you want to call it. And U. All right, they're vectors. I checked those last night instead of doing anything fun. So the scaling variable, so the first scaling variable corresponding with the reduced temperature is basically just the reduced temperature, but U mixes them together. So the 2 different U tildes so I'll call them U tilde. Again, it's just bad notation. So it's 1 plus, 0. What? U minus U star. But the fixed points are 0 and 0, and you have a 0 here. Okay. So that's the direction for one scaling variable, and that the yellow scaling dimension corresponds to this axis, if you will. So U tilde U, great. Okay, so it's just, there's a minus here. I don't know. Call this a constant. This will be minus that constant, R minus R star, plus 1, U minus U star. Okay, so it's, I don't know, like minus R plus U with some constant in front, right? So that's the direction of relevance or irrelevance corresponding to that Y subscript U. That's like the axes of your RG flows. So let me draw 2 cases. So let me label R and U like this. And so R is also UT tilde, right? But this is, say, minus R plus U. This looks like this somehow. Oops. So this should be U. This is the axis U tilde U. Okay, so these are the 2 axes with which the scaling dimension determines relevance or irrelevance. So there's 2 cases. Let's see. If you're greater than 4, okay, so R is always, so it's 2, so it's always relevant. Okay, so you have a fixed point here. That's your 0, 0, 0, so this is always relevant. So your flows look like that. And let's see, is U irrelevant for D greater than 4? Right, yeah. So irrelevance means if you perturb away, you flow back. Okay, so it's like when you're in greater than 4 dimensions, it's like U in the sense of the interactions, the phi-4 term, they don't matter. They don't change anything with regard to this fixed point. Right? And this is like Hamiltonian space. So there's other flows out here. If you're not on these critical lines, you know, these ones look like this. Like this. So if you plunk some random Hamiltonian that you find in whatever your condensed matter, you know, whatever system, you plunk it down here, you just follow the RG flows and it tells you about the fixed points. So this fixed point, if you're in the vicinity of this fixed point, you're on one of these axes. Right? So if you perturb with temperature, you move away. If you perturb with, you know, U, then it's irrelevant and you move back. If you're in dimensions less than 4, then the relevance of R doesn't change, but it does for U. It becomes relevant. Everything's relevant. So you're always just flowing away from this fixed point. Okay, so what does that mean? Stability means, you know, it basically, even if you have interactions, it doesn't matter. So if you're in dimensions higher than 4, that's why your mean field critical exponents are correct. That's why, essentially. Expone. We've seen this many different ways now. But it's like this fixed point controls the physics, even of interacting systems, even of the phi-4 type systems at dimensions higher than 4. But when dimensions are less than 4, the interaction, which is U, or more specifically U tilde or EU, are relevant. So any small amount of interaction, like you would get in an Ising model or anything like that, pushes you away from this fixed point. So that fixed point doesn't control the physics of interacting systems, you know, for dimensions less than 4. Okay? What else is interesting? YT, that gives us nu. We get nu as 1/2. So you see what this fixed point is. Again, it's still the mean field or Gaussian fixed point. So the cumulant, the first order cumulant, you know, it's added this other direction. Okay? But into your diagram, but it hasn't added a new fixed point. We're still dealing with the same fixed point. The Gaussian fixed point, the non-interacting fixed point, whatever you want to call it. Okay, so again, you've added these flow directions, but the relevance or irrelevance hasn't changed the fact that we're still dealing with that same, you know, nu is 1/2, mean field, Gaussian theory. So what we need to change that is the next order in U. Okay, so that's just analysis of the first cumulant. So to get something non-trivial, in that second cumulant, we expect terms, let's just think about what we're going to get. We're going to expect terms that are like u squared here, right? And, okay, so I can imagine something like a u squared, b u squared from the second order. Okay, so part of what we have to do now is solve for that a and b. Let me just write that over here. So once you look at that, especially that second equation for u, you can see that you'll get a non-trivial fixed point. Because I don't want to calculate the second order cumulant unless it's going to change this diagram, right? And you can see that it does. So you'll get something like 4 minus d. I think what will happen is the sign of this thing will actually be negative, but it doesn't matter. So from that equation, you'll get something that, to solve, you'll get the trivial fixed point when u star is equal to 0, but you'll also get something that's like, I don't know, u is 4 minus d over b, right? Maybe minus 4 minus d over b. And I think what happens is this turns out to be negative. So this looks like this. But that's the new fixed point. We'll have to solve for b. So what we're doing is a systematic sort of perturbation theory in the RG equations, the differential RG equations, with this parameter u, right? Because the more cumulants we add, the higher order in u we get. And we did this once already. Remember, we did the Gaussian theory plus fluctuations, and we studied u through dimensional analysis, and argued that u is not going to be a small parameter in that case. So in this case, we're going to have the perturbation theory controlled by u described by this. Okay, so this is called epsilon. So this is the epsilon expansion. Does that make sense? Why should it? I mean, we're going to plug in d equals 3 or d equals 2. That's the only interesting cases. Like d equals 1 is basically trivial. You can solve, there's no non-trivial fixed points. Besides those we've already solved. So if we want interacting theories, like Ising models, then the only interesting dimensions are 2 and 3. And 2, and 3 aren't really perturbative. So this is the epsilon expansion. I mean, that's all I can say. This is the state of the art, essentially, in handling interacting theories, like the Ising model, with analytical field theory techniques. And it basically works. It works okay. What we're doing is in this cumulant expansion, now we're going to develop Feynman diagrams that deal with that second order cumulant. These diagrams have loops and so on in them we have to keep track of. And when you hear people talking about 2-loop calculations and things like that, what they're doing is they're just doing higher and higher orders in this perturbation theory, in this epsilon expansion. Okay, and in many cases, this is controlled, or we understand how we can control this perturbation theory, even for d that are 3 or 2. But in some cases, there's problems. But again, this is basically just the state of the art. Okay, is that clear? Does it make sense? This is where we're going. Questions on this?
There is no after the fact arguments.
So what's going to happen in the epsilon expansion is if you look at the exponents, we're going to get corrections. Okay, so like 1/2 will have a correction at the next fixed point. This fixed point here is called the Wilson-Fisher fixed point. Okay, which essentially Nobel Prizes were given for. So the one that we're working towards, the one we're going to get in the next order. So you get corrections to the critical exponents, and those corrections look like they're getting better because the critical exponents are known numerically, either through series expansion or Monte Carlo, like you guys are going to do. So you just, you look at what this gives, and you look at the exact answer numerically, and it looks like it's working. What happens, though, is if you start doing higher orders in epsilon squared and higher, then you actually start seeing that your answers start getting worse and worse again. And people took a long time to understand that. So, but now they understand. I'll talk about it later. They understand it in terms of resumming a geometric series. And so there's some deep physical reason why these types of perturbation theories give you a geometric series in the critical exponents, which I don't know. So I mean, this is what theorists think about.
So the meaning of small is relative to what? D is a natural number.
Yeah, D's the dimension, the physical dimension of your system.
Is it small because of D, or?
No, it's not small. The point is, it's not small. The epsilon expansion requires the perturbation theory to have a small parameter, but in reality, the parameter is not small. But that's it. That's all you can do. That's, again, the state of the art for interacting systems. It's like this. If you ever done spin wave theory, 1/s expansions, you have Holstein-Primakov bosons, you do 1/s. Then you set S to 1/2. That's not, it's a half, right? It's 1/s isn't all that small. So sometimes these things just work. And if you want to know why, you have to become a field theorist. Okay, so let's do the second cumulant. Okay, so this is this equation, right? So keep track of what we're doing. So we're basically deriving B, and we're not going to need A. What did I write? A over here. We don't need the second order term in the R equation. It doesn't give us anything new. So really we just need the second order term in the U equation here. So we need this term. And then we're going to derive the the differential RG equations and do the same analysis that I just did for this new fixed point, which is called the Wilson-Fisher fixed point. Okay, so we need these averages over the fast modes for that term. It's a huge number of terms. We had A, B, C, and D, and E, I forget, maybe 5 terms for this one. Then we only had to calculate D, and remember there was a combinatorial factor and everything out in front. We carried those through into those equations, right? We got those factors correct. We need to do that for, this is that thing squared that we just calculated. And we also have to calculate this thing, which has also a huge amount of terms in it. So if you think about it too much, you'll just give up. But luckily, people have done it before. Okay, so what do I want to know? So let's just remember the form of this. So there's our U. There's our integral. The delta function, K1 to K4. And then we have these 4 terms, which were fast and slow modes. And that was for K1, K2, K3, K4. So we're going to develop a graphical representation of all the different terms in this second cumulant. And remember, the delta function is momentum conservation. We have all these delta functions that are like K1 plus K2. That one's K1 plus 2, K2 plus K3 plus K4. So will it represent those delta functions by a vertex with momenta coming into or out of them? And so the momentum conservation will be sort of taken care of graphically. Okay, so let's see, I want, U over 4, 2 pi, d, the delta function, let me write it out, K1. That's a dot. And then I'm going to have the 4 momenta coming into it or out of it, the 4 fields. So there's always 4 fields, but they could be slow or fast. K1, K2, K3, K4, like that. And the arrows represent the delta, 1 plus 2 plus 3 plus 4 equal that central point. If I had 2 fields, delta K1, K2 in the delta function, they would just have 2 arrows. And so what happens in that type of term, remember we have slow and fast fields, and so sometimes these momenta correspond to fields that are we have to average over. When we take this expectation value, they're fast, and sometimes they're slow. So let's make them different colors. I'm going to regret this. I don't know which one. Slow fields. And fast fields will be yellow. That's the fields that are associated with a given delta function, if you will. So let me write one example. So if I had u, k1 to k4, let me do too slow. That's k1. And then too fast. Two pi d. Okay, so that would be like, you know, the term that has this, 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 and this, right? Then the vertex representation would be there's my delta function. I got too slow and too fast. What are they? Fast fields are yellow. Okay, so we have tons of these. Basically vertices that we have to organize our calculation with. There's 5 terms in that, you know, A, B, C, D, E, if you look back. In each one of those S ints. Okay? So let me write those. So look back to your notes from last time. A was all slow fields. Okay, so look like this. B was all fast fields. It just gave us a constant, so I didn't care about it. I forget how I did this. Which was, D was the one we kept, right? So D was the one with too fast, too slow. Too fast, too slow. And the other one had odd terms. So probably C had 3 slow. Yeah, so C had 3 slow, and E had 3 fast. I said by Wick's theorem that C and E didn't contribute because they had an odd number of fast fields. Is that right?
Yeah, you were C and E because of cutting those under
yeah.
fields, and D is the only survivor which has coefficient 6.
But so now you have these terms kind of like, you know, inside, you got to square them inside the expectation value and then subtract off the expectation values that you basically already calculated. Okay? So another simplification is once you take the average right? Once you integrate out the fast fields, okay, so say you had, I don't know, yeah, say you had the D term here. When you do the integration, what you're doing is, graphically, you're connecting those two, field lines. Because you're getting rid of the field dependence. You're integrating over it, right? So that's this. Okay, so let's see if that's the one I want up there. Right, so if I average that term, right, so U over 4, K1 to K4. I got my two slows, which aren't touched by the integration. Because remember, the average over fast fields is in the shell lambda over beta lambda. Right, so it only affects these two fast guys. And then you have your delta function. Okay, so that'll be like taking, it's like a D term, two fast, two slows. Let's see, K3 and K4 are yellow. And K1 and K2 are white. And when you perform that integration, you're connecting the yellows. And that's what tells you what conservation momentum looks like. Because the arrows tell you the sign of the momenta. Okay. So these two whites are these two boys here. So the momenta doesn't change, it's still, K. But this one here has only one direction possible, right? So, well, you could, if you draw like this, and we already did this diagram, so we labeled Q, remember K3 had to equal, this is minus K4 equals Q, and then this one is K3 equals Q. Okay, so because K4 and K3 have to be the opposite sign in order to make this loop only have one direction. So that's your conservation momentum that comes from the delta functions. So I'm just graphically doing the term we did last class. And so we know what that was. And these ones here, there's another constraint on the delta function. And we call that one K. So we had something like K and minus K here. Or I think I drew it. You can also draw this one like this. So that's Q. Like that, and then this is K. And then you can say this is K here. Depending on how you do this arrow, right? You can just call it minus K. Yeah, so just look back at what we did last class. So each dashed line here, right, the fast fields. Oh, sorry, each yellow line. Gives us integral. Oops. Over G naught that we solved in the last class. And remember for the, what term is this? The D term, there was 6 of these. So it's 6 times u over 4. And the integral we evaluated was this. Okay, that's from last class. So
What's that minus sign?
what minus sign?
Where you've got on the bottom right leg, it's got minus K.
Oh, just because I pointed it inwards. So yeah, here.
Yeah.
So K2 is minus K1.
Right. It's still pointed in previously as well. In the reverse direction.
Well, okay.
I'm just confused.
Let me deal with those. We're gonna deal with those right now. So if you look at the K, when we evaluated this last class, there's a delta function that gave the momentum conservation for what I'm calling K up there. I just don't want to rewrite everything from last class. So let's do the new terms and look at how all these momentum make sense. So I'm kind of going to do this fast because I'm not making you do this on an assignment. And if you want to do this, you basically have to sit down and do it all from scratch to understand it. But I can give you all the ingredients. You can get the gist of the equations. There's momentum conservation that knocks out a bunch of these terms. So you have to think pretty carefully about this stuff. So let me start drawing diagrams for the second cumulant. And we'll look at these momentum conservation rules more closely. But that's squared. This one is squared like this. Okay. So let me draw this in terms of diagrams. So 1/2. So I got all these things here. Yellows and whites. I'm not going to draw them all, but you're going to get terms that look like s squared. So you're going to get terms that look like this. Plus, wait. You know, all possible combinations of these things, right? You need ones that are just fast, ones that are just slow. And then you have to average over the fast fields, okay? There should be 25 terms there, right? And the second one is two dot products of these things, right? And A plus B, whatever. Each one of those, again, has 5 terms. Okay, so we're not going to obviously write these all out. We're just going to think about kind of the symmetry of the diagrams. So averaging, taking this expectation value, so like in here, it means connecting these legs together, because you got to integrate out those fields in all possible ways. All possible combinatorial ways. So the diagrams will help you keep straight, number one, all the combinatorics that's going into these pieces, and also the conservation of momentum once I'm less sloppy with my K's and Q's. Okay, so I'm not going to do them all, but I'll just tell you how each term goes. So there's many combinations of diagrams and different ways of connecting these legs that don't contribute to the calculation. Just like we argued, I don't know, the B term doesn't contribute in the first cumulant, or the C and E terms don't contribute. So you just have to make note of these. And the first one to make note of is that disconnected graphs. So if I connected this field and this field, so that's how I did the integration, those cancel between the two terms in the cumulant. So let me draw those flat. You know, if you can imagine taking the expectation value of those two terms, that cancels between S int squared and S int squared. It's called the linked cluster theorem. Only linked clusters contribute.
So your dash the black means.
Oh, sorry, yellow. It's dash in my notes. Where did I write dashed? Oh, dashed, yeah. I didn't have a color pen when I wrote these notes. Okay, so this is called the linked cluster theorem. You can draw them all out. There's other ways of seeing it. These disconnected pieces give you, I think, if I remember correctly, super extensive scaling in the free energy or something. So they're unphysical. So you just need connected diagrams. So it's like taking those two on the upper left and connecting those legs together. And I'll draw it like this. So I have these two pieces, and I'm just going to connect them like this, and then keep track of momentum conservation with the arrows later. Okay, so the cumulative expansion is actually the sum of all the connected diagrams. So let's draw all connected diagrams. If we have two, now we have different numbers of fields, right? So if you have 4 fields coming out, that's 4 slow fields. You can have 2, 4, and if you have 6, if you have 8, then you're populating terms that are past 5, 4 in S prime. Okay, so let's organize the diagrams in terms of how many slow fields we have. That tells us how, if we start with 2 slow fields, that tells us how R is renormalized. This one would have four slow fields. But now that we're combining diagrams, we need to consider like two E's together that give us 2 slow fields, right? So we do have to consider all these A, B, C, D, and E's. So that one would look like this. There's 2 of these terms. This is E. How many of those terms occur? Right? Well, they all look like this in the end, but there's many different ways of combining. This leg could go here, here, here. This leg could go at any of the remaining 2, right? So you have to keep track of all the combinatorics of these types of combinations. And when you do that, you get basically the number of diagrams that look like this. Okay, so 6 ways to connect let's see, any 2 lines here, right? This one goes 1, 2, 3, right? 4, 5, 6. So it's like 6. And there's 4 different possibilities for each one of those choices, which leg you start with initially. So it's 4 times 4, right, for each side of the diagram. And I'm going to include the factor of 1/2 from here. Okay, so I'm also going to include this. So you need to know your combinatorics. And that, which is 48, that number goes in front of all of those diagrams. So every possible diagram has a number like that associated with it. Even better, the same starting point on the left results in different topology of diagrams. Okay, so I can also take that diagram with 2 slow fields. And connect some of the slow fields within a diagram to themselves, right? Why not? So that would give me something like 1 connection between them. They have to be connected so they don't cancel between the 2 terms of the cumulant. Do you have a question?
Yeah.
And 2 pieces that are connected within the diagram.
So the only things that get contracted out are the yellow lines?
When I take this expectation value, yes.
Right, I mean, what you've written down on the last line before the bus, it's got 3 yellow lines that need to pass, that's 0.
Um,
6 times 4 times 4 times 1/2 is 48.
Okay.
You've got 2 diagrams, before you join them up, you've got 3 yellow lines going to each.
Right. No, that's what I'm saying. They're only 0 if you took the expectation value of them alone.
Right, okay, so once you multiply them up.
Yeah.
Right, okay.
Yeah. I mean, some of them are still 0. But you have to be more careful with which ones are 0 and which ones aren't. 4 by 4 by 9 by 1/2. Obviously. No. I hope, anyway. There's 72 of these. It gets worse. What's another one? Oh yeah, right, you can have this, and you can have the term that we threw away, the B term, because you can internally connect the B term and then connect different combinations there. So that would give us a diagram that looks like this. Huh. Okay, I figured this out. 4 choose 2, which is 6. 2 by 2. This is just my internal logic. This one happens to have 72 also. Okay, so we're just organizing all the terms so far. I think that's it for terms of 2 slow fields. I can't think of another way of doing it. So now you have terms with 4 slow fields. Okay, so you can have something that's like, I already did one of these, didn't I? Maybe not. So like this piece here, giving a diagram that looks like this. This one can be connected here 2 ways. This one can be connected here 2 ways. There's 6 orientations of picking these, so it's 6 by 6. 2 and a half. That's 36, right? I got another one that's 1 leg. On one side, and then one, 2, 3, 4. So that's 4 fast fields there. That one gives a weird one. Looks like that. The combinatorial term is 48. Now there's terms that we're going to ignore. So just like we ignored the one with 4 fast modes in the first cumulant, there's going to be diagrams that have all fast modes, for example, in the second cumulant. And they could look like they're going to be all yellow. So they could look like this. Or, right, 1, 2, 3, 4, like that. They'll just give constants. And you're also going to have terms, importantly. So that's all, way of 2 fast modes, 4 fast modes. And you're also going to have terms with 6 fast modes. Because you're going to have a diagram that looks like 3 coming in, 3 coming out. So see, what happens when you do this, if you're just thinking about all the terms you're generating here, is you're going to get a term that is higher order in the renormalized fields than 5-4. This is what I told you happens in the 2D real space case, remember? Remember we did real space block renormalization group in 1 dimension, and the Hamiltonian after 1 RG step was self-similar. It was just nearest neighbor interacting. What I said, I didn't do it because it's a waste of time, but in 2 dimensions, the Hamiltonian is no longer self-similar for real space block decimation. You start generating next nearest neighbor, and next nearest neighbor, and so on. So what's happening in the second cumulant for this momentum shell RG is you're going to get terms that look like this, which have 6 slow fields. And those 6 slow fields, after rescaling, just turn into a phi-6 term. So it's like your nightmare. You're generating terms in the action which don't exist previous to that RG step. So what do we do? Why is this okay? Why are we not just quitting right now? Can you guess? So what happens is higher order couplings. So we have R, we have U, we have whatever, U6 for this term. They turn out to be irrelevant. So they just give further irrelevant directions. So even though your RG space starts getting higher dimensional, all of these extra terms like this, which I'll have to show later, become irrelevant. So we don't have to include them up to order U squared. They're going to be irrelevant in respect to this new fixed point that we're dealing with. So that's not obvious. So don't panic on this one. So even though this shows that, I guess you can say the parameter space is enclosed, that it's, what do we call these, scaling dimension. We will show that it's scaling Okay, so that wouldn't be obvious if this was the first time you did this calculation. But again, we're not doing this in historical perspective. So let's write down that second cumulant. Let's just keep track of what we're doing. So it's 1/2 s squared interacting minus s interacting squared. So we have a whole bunch of terms, and you want to keep track of them. 48 of those. 72. Of which ones? Oh yeah, okay. So. These are connected with a fast field here. Did I write this one down? Right. That one. That one, 36 of that one, let's see. What else? That one has 4 fields. That was 44 slow fields. That's 48. I hope you can see the difference between yellow and white. Okay, I think I got these in the right order. 2 slow, 2 slow, 2 slow, 4 slow, and 4 slow. Okay, so this is slow. And this is slow, and this is slow. And that's it. Easy in the end, right? So I've left out all the phi 6 terms, and we just have to now evaluate the integrals for each one of these different diagrams. Okay, so the first 3 terms have 2 slow fields in them. So they give you, after S prime, S goes to S prime, they renormalize, let's see, the R term, right? Because R is proportional to phi squared. But they do it in second order in epsilon. And epsilon's like U 4 minus D. That's what I'm going to call 4 minus D now. So that's that A term. Remember I wrote in the pink, I wrote A U squared. We don't need those in that equation. We don't need those. We don't need this term, or this term to give us the Wilson-Fisher fixed point. So I don't want to calculate them. Epsilon squared. If you're doing high order accumulants looking for different fixed points, which people have done, then you need those, but. Okay, so forget those first 3 terms. So let's look at the last 2 terms. Okay, this one is a weird one. Let's put the momenta on that one. So we have to look at momentum conservation. Remember the vertices are like the delta functions, the thing I'm erasing right now, which would have been useful. So I can label momenta on that last diagram and think about what that means. No, I want slow coming in. Okay, so slow field coming in, then fast, fast, and 3 slows. So K1, K2, K3. I'm not going to write the integral. I'm just going to tell you the answer. So label your momenta somehow. And you'll see that, you know, this one is like the Q, the one I called Q before, I call this one P. In order of momentum conservation at this, right? So this is a delta function of K1, K2 plus K3, K4. I've already identified one of these momenta, or two of these momenta with each other through this Q. Okay, so it means that K1 has to equal P or minus P, right? To satisfy that delta function, whatever way you draw P. But one of those is a slow field, and one of those is a fast field. And the momenta integrals are only defined, you know, 0 to lambda by 2 by b, and then the outer shell, the fast shell, is lambda by b to lambda, right? So that's conservation of momentum, and that conservation of momentum says that that diagram has to be 0. Just lucky. So what I've called K1 is slow, and P is fast. So what did I say? K1 is within the inner sphere, and B is less than P is in the outer. So this diagram after I scared you with all this, the only diagram you need to calculate is actually this one here. This is a kind of non-trivial one that gives you, you know, the b u squared piece in that second differential equation. So that's the one that will give you the piece that gives you a non-trivial fixed point. I mean, you can calculate all these diagrams if you want, but they won't contribute anything to this RG perspective that we're dealing with. And there's conservation momentum here. There's two fast fields. Okay, and we'll start evaluating this diagram and looking at the RG equations. It's actually fairly simple to evaluate, but it'll give us the differential equations that we will analyze. I guess we'll do this after the break.
Any questions on this framework?
So
the absolute value of K1 in the direction of K1?
Where did I write K?
K equal to minus B at the top.
So there's a delta function. So like last class we had that delta function that has, we wrote them as K1, K2, K3, K4. Then we started arguing for why, you know, certain momenta are constrained. Okay, so all the momenta have to, like K1 plus K2 plus K3 plus K4 have to equal 0 coming in there. And so say Q was K2 and K3, or I don't know, whatever, right? So that by drawing that loop, what I've said is K2 has to equal minus K3. So I draw that loop, and there's only one momentum associated with that, and they're related by a minus sign, because it's like delta K1 plus K2, which means K1, or sorry, K2, K3, which means those two have to sum to 0. So it's a vector equation, and it's the same with K1 and P. Okay, so if K1 and KP were, if K1 and P were momenta coming in with arrows in, I might call it K1 and K4, right? They have to satisfy the equation that K1 plus K4 is equal to 0. Okay, so I've just labeled K4 minus P, and so then K1. Oh, maybe your question was much simpler. K1 would be minus P. So those delta functions govern basically all of the, you know, all of the relationships. So I've been very careful because, like, we have to be careful now when we evaluate this diagram. But here I haven't labeled any of them. Question?
The second pattern, or the second diagram, would that be 0 also? The conservation of momentum?
Let me see. I think that one is, yeah. But I'm not 100% sure. Let's see. Yeah, because you have these two equal. Yeah, I think it is. Yeah.
So if you're doing this in QFT, you kind of have an interpretation that these are particles that are exchanging some like force scalar and things like that. Is there another way of looking at this for us, or
yeah, I mean,
more
it's
like the math gives us and we?
I mean, when you calculate the endpoint correlation functions in QFT, you get exactly the same equation here, exactly the same. And the reason is you have a cumulative expansion when you have these endpoint functions, and you just interpret. I mean, you're interpreting these momenta as the momenta of real particles. That's all it is. So, you know, it's the same calculation exactly, but the interpretation here, you know, is just somehow coming from a different place. But the theory is so simple that it's exactly the same. So if you do a 5-4 theory, like when I teach 733, that's the perspective I do. I have 4-point functions in basically the 5-4 continuum. You get exactly the same equation. So you'll see it everywhere. That's why I know what these are, because they're in every book. So yeah, so this is just another place it crops up. So here we're not really calculating like a 4-point function in terms of an expectation value. We're calculating the 4-point function is this perturbative epsilon expansion. But really that's what those expectation values over the fast fields are. They're just correlation functions, right? That's what G0 is. It's the 2-point function, right? So I would say the only, you know, I went through the combinatorics fast, but make sure that 36 makes sense to you in terms of different ways to connect this diagram, because I think this is the most important one at this order. Okay, that's all we're really going to do, I think, with Feynman diagrams. It's just lay this out. So, okay, so let's be more, the momentum's confusing, but we're going to deal with it after the break. I'll talk about the delta functions again, what conservation momentum means, because now we need to calculate this diagram. And from that, we'll get the RG equations, we'll get the Wilson-Fisher fixed point, and probably after we analyze that, we'll move on to something else. Okay, we'll calculate the critical exponents, and maybe we'll look at continuum systems. I wouldn't mind doing the Kosterlitz-Sallis transition before the end of class, since that just won the Nobel Prize. It's interesting to know what a Nobel Prize is worth. This is worth 1 Nobel Prize for maybe Ken Wilson, who figured this out. And so, yeah, why not? You know, all you do is you take the field theory, and instead of Ising, you make it O2. So it's like, you know, it's now a vector that lies in plane. Do the same type of analysis, and in 2 dimensions, you get a Cossett-Salas transition. So there you go. Another Nobel Prize. If you had only done it first, you would get the Nobel Prize.
Amazing.